Okay, so in the next chapter, we'll be thinking a lot more about, fluids in motion and objects moving through fluids, like how do planes fly, how do curveballs and knuckleballs work in, soccer and baseball. But for now, before we get there, let's take a moment to talk about some of the essentials of how pressure works in liquids. There's an important difference between liquids and gases in terms of the pressure within a liquid. And so in this section, we'll think about, how pipes and plumbing work and how liquids respond to changes in pressure. Okay? We'll end by figuring out how straws work, I suppose. So the first section of this, section 6.3.1, is pressure inside a liquid. Pressure inside a liquid. Okay, so to get to address those questions, we need to think more about pressure inside a liquid. And instead of saying liquid all the time, I'm just going to say water, just for convenience, right? And the idea, again, is that, the constituent parts of water obey Newton's laws and, obey conservation laws in exactly the same way that everything else does. And so let's think about what that means in terms of pressure. So to start out, let's suppose I have like a horizontal pipe. Horizontal so that for this first section I can kind of ignore the effect of gravity. And let's suppose I think about a little like parcel of water in some section of the pipe, right? So this pipe I'm imagining is completely full of water, and I'm thinking about just some little section of it. Okay, so again, so actually there's water everywhere, and I'm just considering a little packet, a little blob of water. Excuse me. So if the pressure inside the pipe is uniform everywhere, right? So the pressure of the fluid here is the same as the pressure of the fluid here and at each end of the pipe, then the water won't do anything, right? All of the little bits of water won't feel any net force. And Newton tells us that that means the water will not accelerate, right? Water, just like everything, has inertia. And so if there's no net force on it, there's no acceleration, okay? But if there's an unbalanced pressure, water will begin flowing from regions of high pressure to regions of low pressure. Let's think about that by imagining, like, suppose there's less pressure over here than there is over here. So less pressure and more pressure. So if there's this pressure imbalance, and remember that pressures, pressures are like forces over surface areas. So if there's less pressure, but the width of this pipe is the same, that means that there'll be less force pushing this way than pushing this way. As a result of this pressure imbalance, the water will start to accelerate towards the regions of lower pressure, right? Now, because pressure is force over area, in this case it was important that the surface area of the pipe over here was the same as the surface area of the pipe over on the left side. And maybe in one of the homework questions we'll think about what the consequences are if you have like a pipe that widens. How does the pressure change? How do the forces change? So on and so forth. Okay. Right, so in the presence of a pressure imbalance, the liquid will start flowing. And just like a solid object, this isn't like instantaneous. It follows the consequences of Newton's laws, right? So water at rest tends to stay at rest, and from this pressure imbalance, there's a net force, so the water will start accelerating towards the low pressure. And honestly, this is basically how plumbing in your house and water delivery throughout an entire city works. You have a lot of devices that can locally control or impose like patterns of high and low pressure in different parts of connected series of pipes. And if you can do that, you can basically, orchestrate the flow of water from specific areas to specific other areas as you like. Okay, so by controlling the pressure in a system of pipes, well, that's basically how water distribution in a city works. Excuse me. So how do we create pressure imbalances? So, how do we create unbalanced pressures in a liquid? The easiest way is actually just to try to squeeze the liquid, just to compress it. One of the things that separates liquids from gases, right? So gases, both of these things we said are fluids, but what is one of the differences? Gases have no definite shape or volume, right? A gas will expand to fill whatever volume its container is in. A liquid is different. It has no definite shape, right? It will adapt to the shape of whatever its container is. But it has a volume. It has a definite volume. Right? A given number of water molecules occupy a specific amount of physical space. And you can change the shape of that physical space by putting it in different containers, but you can't easily change how much volume it takes up at constant temperature. Right? So another way of saying that it has a definite volume is saying that water is incompressible. Incompressible. And what that means is that as you vary the pressure, for instance, in water, it experiences basically no change in how much volume of space it takes up. So how can we use this fact to change the pressure inside a liquid? We just squeeze on it. Suppose as a thought experiment we have a bottle of water or soda or whatever with one of those little screw tops, and suppose we completely fill this up with water. Right? There's no air bubbles, no anything like that. It is 100% full of water, and then we seal the cap back on. So what happens when we're just leaving this bottle alone? Well, remember, air molecules are bouncing against this water bottle all the time, and the bottle itself is maintaining its own shape. So the water molecules are also bouncing against the sides of the containers in such a way to balance the pressure coming from the outside, from atmospheric pressure. So when we leave the bottle alone, the water inside is at atmospheric pressure. Which remember is 10 to the 5 pascals at sea level, give or take. Okay, what if we squeeze the bottle, right? So now, in addition to the pressure of all of the gas particles impinging, now we're going to squeeze the bottle, applying a force to it, right? Excuse me. But since the bottle is completely, sealed up and full, and the water itself is incompressible, when we squeeze on it, actually we're not changing the shape of the bottle at all. But we are, applying extra forces to it, and that means that the water molecules inside have to push back against the walls of the bottle harder and harder in order to maintain this balance. So when we squeeze this incompressible fluid, we raise the pressure inside the liquid. Right? One way of seeing that there has to be this balance of forces is, we're squeezing, we're applying a force, but we don't observe any motion, right? So we're squeezing, squeezing this, I don't see anything, but I am exerting a force. So there has to be a force pushing back so that there's no net acceleration, right? So pressure rises when we squeeze an incompressible fluid. I don't know why I keep writing an M. Incompressible liquid. Incompressible liquid. And how does the pressure rise? That's given by something that's called Pascal's principle. So same Pascal after whom these units were named. He studied a lot of things to do with fluids and hydrodynamics and things like this. And what Pascal's principle says is that the pressure in this situation changes uniformly throughout the bottle when we squeeze it. More generally, it says that the change in pressure of an enclosed fluid, an enclosed incompressible fluid, is transmitted to every part of the fluid, and to all surfaces that it's in contact with. Surfaces it is in contact with. What does that mean for our water bottle, plastic soda bottle thing that we've filled with water? So as we squeeze on it, the pressure in the fluid is everywhere getting bigger and bigger, and so the water is pushing harder and harder against all of the surfaces that it's in contact with. And eventually the water bottle will break if we're sufficiently strong. Where is it going to break? It's going to break at the weakest point, which is almost certainly like the small plastic threads holding the cap on. Right? Pascal's principle also underlies the way that hydraulic lifts and hydraulic machines work. Right? So suppose I've got a kind of setup sort of like this, and I'm going to need more space, so let me give it to myself. Suppose I've got a setup kind of like this. I have a tank like so, connected by a thin pipe to a much smaller, much narrower pipe. Okay. And I fill this, the inside of this system completely with water. So, no air bubbles, totally full with water or any other incompressible liquid. Okay. Right. So how is it that you can use hydraulics and apply a small force over here and hold up the weight of, say, an entire car? Resting on, one of these hydraulic lifts. Long arms pushing down. Right? How is it that this is that these hydraulic lifts can work? It's again an illustration of how pressure works, right? So if I look at this figure, what's going on? We are exerting a small force down on this piston. Small force. If the piston is, if we're holding it in place, holding the car up at some certain, height, then the pressure in the water must be balancing out, right, this small force. So the pressure in the water pushing back against the piston from the inside must be balancing out this small force. And remember, a pressure, which is a force divided by a surface area. So the small surface area of this piston multiplied by the pressure is going to give us the force that is going to balance out the force we're pushing down with, right? But this pressure in the fluid is going to be communicated everywhere within the fluid and to all surfaces it's in contact with, right? So the pressure in the fluid is the same, but over here we have, that pressure which can balance out a certain force over a much larger surface area, right? So, a small force applied to a small surface area can be the same as a large force applied to a large surface area, communicated through the pressure in this pressurized fluid, right? So this is another kind of simple machine based on how pressure in fluids work. We can modify, balancing large forces with big forces in the context of playing with the ratio of the areas of these pistons. And actually, in a lot of ways, it's just like, how ramps let us trade smaller force over longer distance for bigger force over shorter distance, right? We could just try to bench press the car directly up, and changing its height by a certain amount would require us lifting the full weight of the car by that height. Here, I have to push this small piston down quite a lot to move enough volume of water so that, that volume of water fills up, lifting the big piston by a certain amount, right? So similarly, here we're applying a small force to a small piston to balance with the force, a big force on a big piston. And if I want to lift the big piston, I have to apply that small force over a bigger distance than the amount this car gets lifted up by. Okay. This is all a way of saying that, when we're operating pistons or water pumps, we're applying forces. That force is equal to, pressures times areas. So the force that we're applying is equal to the pressure of the fluid times an area. And if we're actually moving the fluid, so we're doing work, we can think about the work we're doing in terms of these concepts, right? So, what did I just say? The force that we would need to exert, the force that we would need to exert from this equation would be equal to the pressure of the fluid times the surface area. Now, how much like fluid gets displaced as I move, say, this small piston in this hydraulic setting? Well, the displacement, say, of the water, is going to be the volume of the water divided by the surface area of, say, this piston that I'm pushing on, divided by the surface area. And so from this, I hope that makes sense, right? If I want to know how much do I move an amount of water, that's the amount of displacement is going to be the volume of water divided by the surface area of the water that I'm moving. And we know that we can think of the work done as like the force dotted into the displacement. So in the context of moving fluids around in these pumps, force times displacement is pressure times surface area times volume divided by surface area. So the work done in moving water around is equal to the pressure of the fluid multiplied by the volume of water moved. Okay, so this is another, again, simple machine that lets us, do the same amount of work, if you like, by trading high or low forces over large or small or large distances, but in the context of manipulating pressures and displacements of water within a liquid in some closed system. Okay. The last thing that I want to cover in this chapter is going to be what I'll call section 6.3.2, water seeks its own level. Water seeks its own level, which is a common saying, maybe? I'm not sure. It's a saying anyway. So there's a few key points that I want to go through that might seem disconnected at first, but hopefully by the end of this short section, we'll see where they're all coming from and how they relate to each other. So in the presence of gravity, the pressure in a fluid increases with depth. And you can think about this, if you like, by considering, like, suppose I have, like, a cup full of water. This water has a total mass, and that total mass is pushing down against the base of this glass. So that's a force, pushing down on a surface area. So there's a pressure there. So if I look at the pressure right at the bottom of the glass, it's holding up the whole weight of the column of water above that. And so if I, make this glass more and more full, that weight on the bottom of the glass is getting bigger and bigger. So equivalently, the pressure at the bottom here reflects the weight of the entire column of water above it. The pressure over here just reflects the weight of the water, above that patch of water. So in the presence of gravity, you have these gradients of pressure. This is true, again, maybe we talked about this a few sections ago, like if you've ever dived down into the bottom of a pool, you feel like there's more and more pressure on you because there's more and more weight of the water above you. So it's true of water. That's true of the atmosphere too, actually. It's just that since water is so much denser than air, the effects are a lot more noticeable when you're in liquids. Okay, so what do I mean when I say water seeks its own level, and how can we understand what's going on? Suppose I have like a U-shaped pipe that's open on both ends to air, and it's full of water. Well, if the water is at rest, so it's not moving, we're holding it very still, water seeks its own level means that both of these two surfaces will be at exactly the same height, right? And, if we tilt our U-shaped container, again, it's the height of the water in both parts of the tube that will be the same. So there's the sense that when you have, water that has multiple free surfaces exposed to the same pressure, in this case, these open tubes mean that the pressure right here and right here is just whatever atmospheric pressure is. Water seeks its own level means that when you have free surfaces of a liquid exposed to the same pressure, those free surfaces will be at the same height, okay? Excuse me. One way of thinking about why that should be the case is is by thinking about the fact that, pressure increases with depth. That's an effect due to gravity. So what if it was the case that water didn't seek its own level? So suppose the water was like higher over here and lower over here. Okay, and then what I want to do is consider like 2 points within this fluid, like one that's over here and one that's at the same height but over here. Okay, so if the water is not moving, then it must be the case that the pressures at these positions have to be the same, right? If the pressures weren't the same, we saw above that means there'd be a net force and the water would flow from a region of high pressure to a region of low pressure. Okay, so in principle then, the pressure at these two places has to be the same if the water isn't going to flow. But we know that pressure increases with depth. And in fact, the pressure at this point, is related to supporting the full column of water above it. Whereas this point only has to support, this column of water. So in fact, the pressure at these points can't be the same when you have this, if both of these are exposed to, the same atmospheric pressure. If both those are exposed to the same atmospheric pressure, then the only effects we need to consider are gravitational, and the water can, if you like, lower its total gravitational potential energy by reducing the average height of these surfaces. Some of the water here will flow and raise this surface up, raise it higher and higher and higher while this goes lower and lower until it reaches the lowest average height that's possible. Right? So some of the water from the high elevations will flow to the low valleys. And this basic idea has been used, since ancient civilizations to control the flow of water and supply cities with water. Ancient Egypt, ancient Rome, Indus Valley civilizations, using aqueducts to bring water from a reservoir at some high elevation down to wherever the city is, because water will flow to seek its own level, right? In this way. I guess the last thing that I wanted to cover in this lecture is how do drinking straws work? How do straws work? This is a question that has come up in the question and observations sections of class, and it's also a nice illustration of how these concepts of pressure can be put to use. So first, let's just sit back and think. When we are, we have a straw in a glass of water, and we're sucking on that straw in order to bring water from the glass into our mouths, what is actually going on? Are we exerting an attractive force between our mouths and the liquid? Is there some other force that's pushing up on the straw? What's going on? What's actually going on is, let me draw a jumbo glass, full of water. And we're going to put a smaller straw, like so. And, at first, what is going on? We've got free surfaces of the water, both, in the glass outside the straw and inside the straw itself. We've got free surfaces exposed to the air. And so the pressure inside the fluid is 1 atmospheric pressure, right? What we then do when we're drinking from a straw is, we take our mouths, here's just a blob, I suppose, and we try to suck the air out of the straw. We're not actually like sucking up on the water. We're just trying to remove as much of the air that used to be inside the straw as possible, right? So now we've got a new situation, right? We've got a system where it used to be the case that the atmosphere needed to be exerting 1 atmosphere of pressure in order to keep the level of the water in the straw the same as the level of the water everywhere else in the glass, right? But now we go ahead and remove, all of the air molecules that were supplying that pressure needed, right? So now there's an imbalance in the pressure in the liquid. The water everywhere in the glass is experiencing, over here, say like at the surfaces, that's experiencing 1 atmosphere of pressure, but the surface of water inside the straw is no longer experiencing 1 atmosphere of pressure. And if we sucked all of the air out, we would be removing, all of the pressure from the air. So what happens when water experiences an imbalance in the pressure? it starts to flow. So because there's no longer any pressure balancing the pressure outside the straw, water starts flowing up. It starts accelerating, towards our mouths. As water rises up the straw, the weight of this column of water inside the straw starts to increase, right? So, when the water, let me draw just this straw now in a few stages. So at first, before we suck any air out, there's an atmosphere of pressure at this level, and that's what would keep, everything nice and happy, right? Because there's an atmosphere of pressure at the other surfaces at the same height, okay? So now I take away the air in the straw, so now there's no longer any pressure from that, and the water starts to rise, and it will keep rising until the pressure of the column of water inside the straw above this free surface is able to replace the entire pressure that used to be supplied by, molecules of the atmosphere, right? So that's what's going on when we drink from a straw. We create a pressure imbalance, water starts to flow as a result, and this argument actually tells us that there's a biggest size that a straw could possibly work. You see, water will only flow upward, above this point, as long as the pressure here is less than 1 atmosphere, right? But if I stack a big column of water right here in this straw, the weight of the water is supplying a pressure, this surface area of the straw supporting the weight of the water above it. So how tall a column of water? Column of water would correspond to 1 atmosphere of pressure, 1 atmosphere, which is about 10 to the 5 pascals. This would set the biggest straw you could possibly use and still be able to drink out of. By thinking about this, maybe pause the video for a sec and figure out if this is the target pressure we're trying to think about from a column of water, how tall a column will that be? Now that you're back, or never left, I'm sure, using the fact that, for instance, the density of water is about 97 kilograms per meter cubed, and given that this is our target pressure, so remember, the target pressure is going to be a force over a surface area, and the force is going to be the weight of the column of water, which is going to be the mass, which is going to be this density, rho water, times volume. So that's all the mass, times the acceleration due to gravity. So if this is the equation I'm trying to balance out, so pressure, target pressure of 10 to the 5 pascals, I want that to be equal to 997 kilograms per meter cubed. That's the density times the volume. And let me write the volume of water as the surface area times the height, and then times g. You can see that I've written the volume in that way, so that surface area cancels out. And what I'm left with is just trying to solve 10 to the 5 pascals is equal to 997 kilograms per meter cubed times this height that I don't know, times the acceleration due to gravity, and the answer is about 10 meters. So if you had enormously powerful lungs and you're actually able to suck out all of the air inside of a straw, even still, you would not be able to drink out of a straw if that straw was 10 meters or 30 some odd feet. Good to know.